So up till now, we've done a lot with limits. We've had answers where the answer is infinity, but we've never done any where x is approaching infinity. And that's what today's lesson is. And so think about what that means as x is approaching infinity. It means as x is getting infinitely large. So if you look at that table there, look at example 1, you see that table? So in the past with limits, we would converge onto a single number as we go inward. Well, now we're going to look what happens as we go outward. Okay? So what is y approaching as x is getting really large in the positive or negative direction? So x can approach infinity or negative infinity. And when we started limits way back when, probably the second day in this class, we used tables to get the answers. And we're going to do that same thing here. So I want you guys to enter that function, and I want you to fill out this table, and we're going to look at what happens as x approaches infinity and negative infinity. All right, so go ahead and punch in that function. Just remember to put the denominator in parentheses. And then fill in the values in that table. I might go to that calculator conference in Chicago. It sounded really cool.
Is it on your on the recording right now?
Yeah, it's gonna record everything.
Okay.
Until I'm done.
Are you gonna edit it or you just gonna
No.
put it all on there?
Yeah, I'm gonna say good
You're
luck.
too lazy to do that.
I don't know how to do it. It's not that I'm too lazy. I know how to click start recording, and that's about it. My other option, I could have just made the video yesterday on my prep, or well, it had been Friday on my prep, and it could have cut out all this stuff, but I just didn't. Figure I'd just do it now.
So those goal did it tell like 10 minutes of we just talking to Conroe was talking about it?
No, I started it after. What? Yeah, right. Fill out that table.
Oh.
Make sure you put that denominator in parentheses. You know what I forgot to give you guys? Is your take-home quiz.
It looks kind of scary with all your rules on Canvas.
Yeah.
It is scary.
Fantastic.
This is due, what's today? Tuesday? This is due Monday. So in 2 class periods. What rules are on there?
Also scary.
Don't ask a math teacher for help.
Yeah, don't do that.
What about a student?
Yeah, that's fine.
But it's like, it's doing 2 cycles. Don't ask a math teacher for help. Must show work on every problem before we get it.
Those
And
are-
there's a second part.
Yeah, the in-class quiz.
That's scary.
Huh?
Holy.
Sure.
This is a.
He said sure.
This is a.
I said sure.
Okay, sure.
Okay.
This is like a mini. This is a.
Good talk. Alright, so here are the values you should have gotten. If you didn't get these, make sure you enter the function correctly. But
I didn't.
you didn't get those?
I got 2. I got 2 for 1,000.
Oh, did you?
Yeah.
Oh man. My calculator must be better.
Probably.
Ooh. I'm just kidding. So, but again, we're focusing on what's happening as x is approaching infinity and as x is approaching negative infinity. And so, look at what's happening as x is approaching infinity. Now, say as x gets really big, what is y approaching? 2. So, for that question where it says find the limit as x approaches infinity, we would say equals 2. We're just looking at what the y value is as x is getting really big. And as x is approaching negative infinity, we're also approaching 2. And if you think back to Algebra 2, and I'm sure you talked about horizontal asymptotes in pre-cal as well, really what you're looking for is what is the horizontal asymptote? That's what a horizontal asymptote is. As x gets really big, what is y approaching? So these questions are just saying, what is the horizontal asymptote of this expression? It's the same question, just posed in a different way. So there were 3 horizontal asymptote rules, if you remember. Remember the 3 horizontal asymptote rules? Anybody remember one of them? Kylie?
If the highest exponent of the numerator and denominator are the same, then you just divide their coefficient.
Yeah. If your degrees are equal on the top and bottom, so like you have x squared and x squared, then your horizontal asymptote is just what your leading coefficient fraction is. So in this case, it would be 2 over 1. So 2. So if your degrees are the same, it's just your leading coefficient fraction. You guys remember that? I know I taught it. But, do you remember that? Oh, good. Good job, Jack. All right. So, a theorem. It doesn't have a name. It's the nameless theorem. If R is a positive rational number and C is any real number, then the limit as x approaches infinity of C over x to the R equals 0. Basically, if you have a number over x to some positive rational power, so x to the 5th, x to the 2/3, x to the 1/2, x to the 1/millionth, and if you take this limit as x approaches infinity, you're always going to get 0. Why are you always going to get 0 when this happens? Try to think mathematically. Instead of trying to memorize rules and theorems, why is this always going to equal 0? We're just busting calculators left and right. Why is this always going to be 0? What happens as x gets really big? Yeah, but what's 2 divided by 100?
1 over 50. Wait, 2 divided by 100?
Yeah, as a decimal.
I don't know.
Do it in the calculator.
Okay, thanks.
2 divided by 100.
0.02.
0.02. What's 2 divided by 10,000?
2 to the 10. Wait, 2 times 10 to the negative 4th.
2 times 10 to the negative 4th. So 0.0002. What's 2 divided by 100 million trillion?
I don't want to do
What's it really close to?
Yeah, but what are you
1
putting-
million, right?
What's 2 divided by 100 million gazillion billion bajillion?
Negative infinity?
Oh no.
Stop asking me.
Connor, what's it getting really close to? 0. Getting really close to 0.
Great.
Because you have a number over a number that's getting really big, and so if you have like 2 over a giant number, you're getting really close to 0. That's what this theorem is saying. Is that bottom number is getting really big, and you have a constant on top, which means that fraction is getting closer to 0. That's what that theorem's saying. And same idea if x is negative. So if x is a negative number, same idea. The limit as x approaches infinity of c over x to the r is also equal to 0. But basically, if you have a number over an x term with a positive rational power, you're always going to get 0. That bottom is going to dominate the top, is what's happening. And the fraction is getting closer to 0. So with that said, if you guys remember some limit rules, if you have, look at example 2 here. We have the limit as x approaches infinity. And if you remember some limit rules, if you have the limit of a difference, you can rewrite that as the difference of the limits. Meaning you're allowed to, a limit is not a number, but as far as rules go, you can kind of distribute that limit into both and then subtract what you get. So let's think about what each of these individual limits would be. All right? Oliver, what's the limit of 5 as x approaches infinity?
5.
Just 5. One of the very first limit rules we learned is if you take the limit of a constant, regardless of what x approaches, your answer is 5, or whatever that constant is. Because if you would graph the line y equals 5, well, as x gets gigantic, y is still 5. So that limit is 5. Olivia, what is the limit of 2 over x squared as x approaches infinity?
0.
It is 0. Because think about, that's using that theorem we just learned. As x gets gigantic, think about having 2 divided by a gigantic number, it's getting really close to 0. So as x approaches infinity, when you have that x in the denominator, constant on top, this is 0. So 5 minus 0 equals 5. You don't have to split it up. I mean, you can kind of plug the infinity in. Now, I say that term loosely. You can't plug infinity in. But if you plug infinity into the x, all the x's, you can kind of see what happens. If you plug this infinity in to this x right here, you're going to get 5 minus, and that's going to become a 0. So you don't have to split it up, but just reinforcing some rules that you're allowed to do. So example 3. Well, now we have an x on top, x on bottom. And my first thought, let's plug infinity in. Okay? Let's plug infinity into the top. Let's plug infinity into the bottom. Okay? So if we plug infinity into the top, what's the top going to approach? Jack, what's going to happen if we plug infinity into the numerator? What's the top going to become or approach? The numerator, yeah. It'd be infinity. Yeah, if I plug a gigantic number in for x on top, I get 2 times a big number plus 3. If I plug an even bigger number in, I get 2 times an even bigger number plus 3. Essentially, that top is growing infinitely large. So we get infinity on top. And if I plug infinity on bottom, what's going to happen? What's it going to approach? Arturo, what's the bottom going to approach if you plug in infinity? Infinity also. AJ, what's infinity divided by infinity? So this is where there are various degrees of infinity. Infinity divided by infinity is not 1. This is actually called an indeterminate form, which up till now we haven't approached this. The only indeterminate form, I'll write this, the only one we've approached so far is 0 over 0. Indeterminate form. That means it's inconclusive. Your indeterminate forms are infinity divided by infinity. You can't conclude anything. And 0 over 0. When those cases happen, you have to do other analyzations. You have to do something else. And so here's what we're going to do. I have a little typo here, but it says divide every, should be a y there. Divide every term in your problem, every single term. So the 2x, the 3, the 3x, the negative 1. Divide every term by the highest degree variable from the denominator. This is how we're going to eliminate this issue. So what is the highest degree variable in the denominator?
1.
So the highest degree is 1, right? So x, is that what you meant? The highest power is 1?
Yeah.
Yeah. So x to the first. So we're going to divide every term in here by x to the first. Okay? Everything by x. And look what happens. So I'm going to divide the 2x by x, the 3 by x, the 1 by x, the 3x by x. We're dividing every single term by the highest degree variable from the denominator. Well, let's see what happens here. So now we're going to have the limit as x approaches infinity. Well, the top now is going to become a 2 plus 3 over x over, now we have 3 minus 1 over x. Now let's try to plug the infinity in again. So if we plug infinity into the numerator now, what's the numerator going to become? Well, let me back up. What is 3 over the infinity going to become? If I plug the infinity in for this x here, Hiba, what's 3 over infinity going to approach?
0?
0.
Okay.
You have 3 over a gigantic number. 3 over infinity is going to approach 0. That's going to become a 0. 1 over infinity on bottom is going to become a 0. So what are you left with? 2/3. Which, using your horizontal asymptote rules, which is what Kylie had said, look at the very beginning of the problem. Those degrees are equal, which means your horizontal asymptote is the leading coefficient fraction. It would have been 2/3 right off the bat. So when you come up with these questions, you don't have to go through this process of dividing by the highest degree variable from the denominator if you remember your horizontal asymptote rules. When you get these questions, if ever I see the limit as x approaches infinity, I immediately think of this question as saying, what is the horizontal asymptote of this expression? That's how I transform this question. What is the horizontal asymptote? It is 2/3. I want you to take out your graphing calculator. I want you guys to graph that expression, the original expression. I want you guys to graph it. So the 2x plus 3 over 3x minus 1. I want you guys to see a visual here. And then understand what the question's asking and what you just found. So as x approaches infinity, look what's happening. I'm really saying, what's the y value getting close to as x gets way out here? And our answer was 2/3. You could see it come to life on the graph. Right about here at 2/3, you have that horizontal asymptote occurring. So as x is getting gigantic, it's just saying, what is your horizontal asymptote? What is y approaching? Same would be true in the negative direction. If it said, what's the limit as x approaches negative infinity, you'd get the same answer of 2/3. Okay? All right. So this one, the limit as x approaches infinity of 4x plus 7 over 9x squared plus 2. So my first thought is, let's plug infinity into the top and the bottom. So if I plug infinity into the top, I'm going to get 4 times infinity plus 7, otherwise known as infinity. And if I plug infinity into the bottom, Anthony, what's infinity squared?
I have no idea.
Ben, what's infinity squared?
Infinity.
It's infinity. Ben, what's 9 times infinity?
Infinity.
What's infinity plus 2?
Infinity.
Oh, you're good. So we get infinity on bottom also. Now I heard Olivia say super infinity because there are various degrees of infinity. What? You don't like that, infinity? It's bigger than the top. Because it's going to get bigger quicker, is what I'm trying to say. So there aren't really various degrees of infinity, but things can approach infinity quicker, is the way that you're thinking about that. So we have an indeterminate form here. So let's use the approach that I just talked about on the front side. Divide every single term in this fraction by the highest degree variable of the denominator. Anadoris, what is the highest degree variable of the denominator? Yeah, so we're going to divide everything by x squared. So divide by x squared, divide by x squared, x squared, x squared. So now we have the limit as x approaches infinity of 4 plus 7 over x squared. Oh wait, it'd be 4 over x. And then on bottom you'd have 9 plus 2 over x squared. Anybody know why we try to get rid of the highest degree variable in the denominator? Why we do this? Why does it work out? What's happened both times we've done that in the denominator?
Now both the top and bottom are the same term. Like, they're both x squared.
Like get a 0 on bottom.
Well, yeah, that's the big thing. Well, not so much that you can't get a 0, but what won't you get?
Infinity.
You won't get infinity on bottom now, because what's left is a constant here. You have a 9 right here. That's why we divide by the highest degree term of the denominator to try to get left with that constant right here. And so now when we plug infinity in, that fraction becomes a 0, but you still have that constant to play with. So that's why this is working. So if I plug infinity into the top, 4 over x is going to become a 0. 7 over x squared is going to become a 0. 0 plus 0 is 0. On bottom, the 9 stays, but 2 over infinity is 0. I shouldn't say 2 over infinity is 0. We're still talking about limits here. You're not allowed to plug infinity in, but you're looking at the limit as x approaches infinity of every single term. So they become 0. And then you get 9 plus 0 on bottom. Olivia, what's 0 divided by 9? 0. Who remembers this horizontal asymptote rule? So the first one Kylie said was, if the degrees are the same, then your horizontal asymptote is your leading coefficient fraction. What's this one? Huh, Hibba? Did you whisper something?
No, I said sorry because I hit her foot.
I got excited. I thought you were answering the question in a whispered tone.
Is it just that if the bottom is bigger, like the x squared,
Yeah.
the exponent, then it's 0?
Yeah, always. If your bottom degree is bigger than your top degree, then as x approaches infinity, your limit is 0. Your horizontal asymptote is always 0. So those are the two of the 3, I should say, that you guys learned back in Algebra 2, and hopefully pre-cal. All right, example 5. Let's plug in that infinity, baby. So on top, Hibba, what's infinity cubed?
Super infinity.
Super infinity. In general, on top you're going to get infinity. On bottom you get infinity. Infinity over infinity is indeterminate. So we're going to use that process of dividing every term by the highest degree variable of the denominator. So in this case, let's divide everything by x squared. X squared. X squared. X squared. X squared. We have the limit as x approaches infinity of 5x minus 3 over x over 2 minus 1 over x squared. Now when we plug in infinity, Zach Homer, what's the top going to become?
5x. Oh, you
But-
mean like that term?
If I plug infinity into the numerator, what do I get in the numerator?
0? You mean for 3 over x?
Nope,
Or-
for the whole numerator.
Oh, infinity.
Infinity. Because 5 times infinity would be infinity, and then minus 0. So infinity minus 0 is infinity. So you get infinity on top. That's okay here, and you'll see why. On bottom, what do you get? What's left on bottom? Jake Harrison? 2. Alec Anderson, what's half of infinity? Infinity. So you actually do get an infinity answer here. And if you graph this, I'm going to graph this and just show what's happening here. So I'm going to graph. You can too if you would like. 5x cubed. Sometimes it's just fun to graph things in your calculator. No? Just me?
Yeah.
Okay. This one looks really cool if you watch a graph. Got a little slant asymptote in there. You guys remember slant asymptotes? But graphically, think about what's happening here. As x gets really big, so as x goes out to infinity, y is going up without bound. It's going up towards infinity. So that is graphically what is happening. Now, some people will say the limit doesn't exist. Technically, the limit does not exist. Because when you limit towards something, you should approach a number. But oftentimes when these questions are asked, they're talking about graphical behavior. And so oftentimes they'll want the answer of infinity, not does not exist. What I've been told, and I mentioned this back in the limit chapter, is they're never going to pit infinity and does not exist against each other on multiple choice. Like you're not going to have to make the decision on which one to put. So if it's free response, I would personally accept both, but really what they're wanting is the answer of infinity. If this is a multiple choice question, the answer is probably going to be infinity. All right? There it is. So what is the third horizontal asymptote rule? The first was if the degrees are the same, then it's the leading coefficient fraction. The second is if the degree on bottom is bigger, then it's 0. What's the third one? Yeah, if the degree on top is bigger, then there's not a horizontal asymptote. It's going to be increasing or decreasing without bound. So that's your third one. And in fact, going back to Algebra 2, if your degree on top is 1 bigger than the bottom, there's actually a slant asymptote. And you'd have to do the long division to find the equation of the slant asymptote. And you can actually see that slant asymptote taking place. You see that slanted line that your graph is approaching at the extremes. You guys remember that? You guys remember anything? Why was I talking 2 years ago? 3 years ago? All right. So those rules are in place for rational functions, meaning polynomial numerator, polynomial denominator. Those rules don't apply when you get into some messy situations like we have right here. So rational functions will always approach the same horizontal asymptotes towards infinity or negative infinity. That means all those questions I asked you, like example 4 here, had I said x approaches negative infinity, the answer would still be 0. On example 3 right here, had I said x approaches negative infinity, the answer would still be 2/3. These are rational expressions. But for non-rational expressions, I want you guys to look at this. I want you guys to do this. I want you to graph it, all of you. Don't wait for me to do it. Do it. Graph this expression. And I want you to look what happens as x gets really big to the right and really big to the left. This is a fun one. So first I just want you to notice that there's not one horizontal asymptote. Okay, so your horizontal asymptote rules technically don't apply because there's not a horizontal asymptote to this. Like there's not one horizontal line that your graph is approaching at the extremes. As x approaches positive infinity, you get one answer, like y is limiting towards something. We got to figure out what it is. And then on the left, as x approaches negative infinity, y is limiting towards something. We got to figure out what that is. There are 2 different answers to this question based on what the question asks you. Okay? So let's figure out how we attack this. 2 years ago, I taught this problem very brutally. It was awful. I taught it, and it didn't even make sense to me when I was teaching it, let alone the students. And so I took my key. You can kind of see it. I whited everything out that I did. You see that white out. See it where it's glistening? I was like, that's terrible. So I taught it a different way. And I think this way makes more intuitive sense. So on the bottom here, you can't square root an expression if there's a plus sign here. Meaning you can't square root each of these terms individually. All right? Like this would not be x plus 1. Not allowed. But since we're talking about these x's here, does anybody know what the square root of x squared is? What's the square root of x squared? X? Anybody have a different answer? Because it's not x. What if I said this? What if I told you the square root of x squared is not equal to x? Think about that. Why? Why is the square root of x squared not equal to x? It's not. Or am I lying to you guys? I'm not lying. Oh, I'm not going to do that. Anybody know why? What if x was negative 3? What if I did this? What's the square root of negative... So x is negative 3 here. What's the square root of negative 3 squared? It's 3. So it's not what x is. X is negative 3. So it's not x.
Absolute value.
The absolute value of x. So the square root of x squared is not x, but it's actually the absolute value of x. Yeah. So with that said, understanding that, okay, I want to jump back to the problem. If I'm looking at these, okay, as x is approaching infinity, these constants are really irrelevant to whatever is happening. Like all these problems we've done, when you have that constant over an x or whatever, those constants have been completely irrelevant And the only thing we actually care about are the leading terms. That's what matters. We're analyzing the leading terms. So same's going to go for these problems. I don't care about this 3 and this 1. They may as well not even be in the problem. What I care about is what's happening with this 4x and the square root of x squared. So I'm going to rewrite this problem as the limit as x approaches infinity of 4x over the absolute value of x. Right here. So now as x is approaching infinity, what is this expression going to approach? Just think about this and just analyze it. As x gets really big, what is this fraction going to become really close to? If you plug 10 into both those x's, what does that fraction become? 4. If you plug 100 into both those x's, what does that fraction become? If you plug 100 billion quadrillion million, what does that fraction become? 4. So what is this limit equal? 4. Now, the negative infinity one is where it gets a little different. I'm going to do the same thing. Cross out the constants. And we have the limit as x approaches negative infinity of 4x over the absolute value of x. What's going to change? What's going to happen on this? What do you think? Why is this? Yeah, the sign's going to change. Why? Yeah, the top now, when I plug negative numbers in, if I plug negative 10 in for x's, I'm going to get negative 40 on top, but the bottom is still going to be positive 10. The bottom's always going to be positive. The sign changes, essentially. And so this is going to be negative 4. So you have to think about what happens if I plug negative numbers in. So that's a negative, that's a positive. That's why you're getting 2 different limits, and graphically you can see that happen right here. As x approaches infinity to the right, that graph's approaching 4. From the left, it's approaching negative 4. But again, a couple things to consider here. First of all, you have to know the square root of x squared is not x, but the absolute value of x. The next thing you need to think about is those constants on the end are completely irrelevant when you're talking about x getting gigantic. So that's why I'm allowed to cross them out, because they play no part in this problem. I really care what's happening with 4x over the square root of x squared. So 4 and negative 4. I taught that way different 2 years ago. I don't even know what I did, but it was bad. All right. Last 2. Find the limit of sine of x as x approaches infinity. I want you guys to answer these 2 questions. I want you to answer them. You can talk to each other if you want. Don't graph them. I want you to answer those questions. Please. Thank you. Ooh, great discussions going on. My coffee is cold. It no longer tastes good. I don't like sitting here the whole time.
It's weird.
Boring for me.
It looks like you keep like rocking that, like you're gonna get up, and then you sit and like sit back.
I don't like it. Some teachers teach this way the whole time. Math teachers just sit at the smaller times. Like if you on my prep, I walk around. Most teachers do.
That's so boring.
I agree. I'd be less tired if you guys.
But you won't get a good workout in either.
I don't think what I'm doing is a good
Well,
workout
it's
anyway.
like activity.
Yeah, that's true, but
So you get some steps.
I don't think that matters.
I think I just feel lazy if I sat down.
Yeah.
feel like it counts.
I think steps are overrated.
At least you're moving.
Like walking, I feel like walking doesn't do much. Am I wrong?
They're doing
Is
something
this all on
though.
the video, or did you pause it?
I don't know how to pause.
They're gonna hear all these conversations.
Yeah, I mean, I don't know.
No, I sound stupid on there.
And you're gonna be on there for years to come.
Exactly.
Because I'm gonna have this on Canvas for as long as I teach this class.
Wait, for real?
In 20 years, my students are gonna say, "Who's Hiba?" But you're cemented in history, though.
Yay.
All right. So I'll put these answers up.
Does not exist.
First one is does not exist. Now I said on the other ones, you could either say infinity or does not exist, but that doesn't apply for this. Because that sine function oscillates between -1 and 1. It never approaches infinity. It doesn't approach anything ever as x gets really big. There is no limit to sine of x. But the second one's a little different because if you would think about the limit of each thing, top and bottom, if you would plug a number into the sine function, you're going to get a number between -1 and 1. In other words, for that part B, that top is always going to be a constant. You don't, and now it changes as x changes, but it's always going to be a number between -1 and 1. So the top is a constant. The bottom is infinity. And we talked about that original theorem. If you have a constant over infinity, then it's approaching 0. That limit's approaching 0. So while both of these have a sign in them, they are different. And now also look at, so Hiba mentioned the rules for limits. She said there was 2 of them, and she was asking about them. Back in chapter 1, one of the rules you had to know was this. Remember what it equaled? 1. But notice you have the same expression inside the limit, and they're 2 different things. That's because it does matter what x is approaching. Some people back in chapter 1 just thought, well, anytime you see sine of x over x, it's 1. Well, no, it's as x approaches 0, you get 1. This one's different. So you have to treat that problem differently. All right. So just to end with some rules of thumb, if you get an AP-style question and you see the limit as x approaches infinity, you don't have to divide every term by the highest degree of the denominator. It works. It's the analytical procedure. But really, they're just saying, what is the horizontal asymptote? That's the question they are asking you. They're seeing if you know your horizontal asymptote rules, which are as follows. If the degree of the numerator is less than the denominator, the limit is 0. If the degree of the numerator is equal to the denominator, then it's the leading coefficient fraction. And if the degree of the numerator is bigger, then the limit doesn't exist. I would think about, is it approaching positive or negative infinity, because that's probably the answer they're going to want. But you'll never have to decide. Questions on limits as x approaches infinity? You guys have been a great audience. Thank you. My recording is not stopping. If this did not record, I'm going to lose it.
Well, yeah, log 7.
Oh! It says start recording. When done, push escape, then the stop recording button. I pushed escape. Stop recording button did not show up.
Try turning it off of that.
No! I've done this before and it's worked. This is ridiculous.
We just want. He just really wants that because it's hard in there.
Every time I push escape, it will say stop recording.
How do you start recording?
There's a button that says start recording and it's a red button. And then when you push escape, it comes up again and you click stop recording. Image mate. I've done this before.
I know they're being used.
They get call tags.
I'm gonna call my wife.
Oh.
Oh yeah. So cool.
Texas.
I don't know how the program works.
You're gonna try to help us, so that matters.
Because they want things like I'm saying like the
She did not pick up.
We can run down there.
If she was in her room, she would have picked up.
His phone conversation.
Does it say it's still recording?
I don't know if it's recording or not.
I really hope it was.
Hmm. I don't know why when I move this, that screen still lights up. Hmm. That didn't work. I don't want to unplug this cord.
Yeah, probably be bad.
But everything I've recorded should already be recorded, right? Can't.
If it did record, yeah.
But I'm saying if it did record, it would do no damage to unplug this right now, right?
Depends on how it's programmed. But yeah, probably.
I always push escape, and then it pops up and says stop recording. Yeah, feel free, man. You do have homework and a take-home quiz.
What does Mr. Pierce have to say? Oh my god. Maddie and everyone. Hey.
Oh.
Yeah, okay, we know. This doesn't help.
You just remind me, probably.
Yeah, I needed the reminder. I need to start writing it. Wait, why do we need? Why do we need what? Oh, quoted. Okay, I thought we needed. How many passages? I was like, I have two. You have two. I have two body.
Did it record?
Wait, you only have 4 quotes total. Yeah.
Uh-oh.
4, right?
Are you really gonna do that?
Yeah.
No.
I texted you and asked.
It could be the only thing we can do,
Yeah, I know. I
though.
replied.
Because I don't.
You better.
But it won't let me then save the recording.
Okay, so it won't let you save the file anyway. Why? Did it actually capture? So confused. This doesn't. Usually, when you like exit out, it's like, do you want to save? But it won't even let you save the file right now.
What happens if you push the exit out? Did you do it?
That happens.
Well, that's not good. Okay, but you might get lucky.
I know. I'm hoping.
How dare you? I mean, it's fine if I have to do it again block 7. I just want to make sure it works when I do it block 7.
I don't know.
Why is that lighted up box still there?
Because technically we haven't exited out of the program itself yet. We just exited out of that window. So I'm gonna just.
I mean, it's going to delete it.
If you disconnected, could you?
Why is
Wanna
that
save
window
it?
still there though? That's weird.
I feel like you have to disconnect it.
Okay. That's probably it. But
And then it will just
I-
save it, right?
let me
Or
just.
like ask.
Yeah,
Oh,
it's
it's
gone.
just gone?
Yeah.
Yeah, it's gone. Let me. How do I get that back up? Where's the program?
It
Oh,
was
I can.
ImageMate and QuickTime. They work together somehow.
Okay. Let me pull this back up.
Oh, it's still there.
No,
Oh no.
that's
Okay.
that would be a new recording.
Hoping that it's gone.
Oh, that just captures a. It's weird.
I know. I'm kind of upset now.
You would have had a legacy.
I swear.
Is it not there?
Shoot.
We exited the
Yeah.
program, but the lighted up box won't disappear now.
Did it turn off the album?
Turning off the Elmo when. The only thing I could think of would be. Yeah, I guess we could turn off the Elmo and see, but. Yeah, it doesn't.
Oh no.
Unplug it and see what happens. That's weird.
That was a funny video.
What does it do?
You should have just let it run until it was.
I don't know.
Then you could have cropped it.
Maybe that'd be a long video, but I mean,
Or you could have told them stop watching at 15 minutes.
probably have to turn it off, turn it back on.
Let me just reset it real quick.
Do
Or
you
restart.
have to turn that off now?
For what?
The video?
You don't have anything that's not saved that you don't want, right? Before I do
No.
this? Okay. So I don't want you just to lose it.
Oh, you got a message.
Oh! There you go. It did save.
It did?
It did record.
No.
What?
It did. When I started restarting the computer, it's like, do you want to save this?